In this clip, we'll focus on calculating the normal. We'll look at the 5 kilogram block in 3 different instances, and we'll try to calculate the normal in each cases. If you have not tried these problems yet, please hit pause and try them before we start looking at the solutions. So let's focus on the first problem. So we have a force F1 that is pointing down on the block. So first thing I advise you to do to be able to identify the forces is just to draw a circle around your object, and every time there is a contact, you know that there will be a contact force, at least one contact force. In here, the other contact force that we have, in addition to F1, will be the one with the ground. So in this case, this is the normal. It could also imply having friction, but in here we don't need it. Then we can think of long-range forces, and the only long-range force that we have in here would be the force due to gravity. So this accounts for the 3 different forces that we have in here. So I can redraw these on my axes to draw my free body diagram. So I will have Fg, and it turns out that Fg in here will be just slightly bigger than F1. So we also have F1 in here. And you can see visually right away that we will need Fg and F1 to essentially be cancelled by the normal force. So my normal has to be a little bit bigger than both of these. So right from the graph, we can see what's going to happen. And then we can use Newton's first law, so sum of forces. In here, we focus on the y-axis, is equal to 0. And this tells us that the normal, positive because it's on the positive side of the axis, minus Fg, which is on the negative side, minus F1, will be equal to 0. So right away we can see that the normal will be equal to the sum of Fg and F1. Fg, we know, is just equal to the mass times the acceleration due to gravity. So we can just plug all the values in there. We will have the mass, which is 5 kilogram, times g, which is 9.80 meters per second square, plus F1, which is equal to 40 newtons, and kilogram meters over second square, that's also newtons. So what we will get in the end in here is this will be equal to 49 newtons, plus 40 will bring us to a total of 89 newton. So you can see that indeed the normal is greater than Fg in here, which is not surprising because F1 is pushing down on the block. So the normal has to compensate in order to keep the block at rest. So next we will look at the block that is on the incline, and the block is at rest. That's important. So same deal as usual, draw a small circle around your object. Once you have that, identify contacts. Here we have just one contact at the bottom. So this contact is between 2 surfaces, so we know that there will be a normal force, not surprisingly, as that's what the question is asking. But also in here we will need the friction force that will keep the block at rest. Without friction, the block would not be at rest. And finally, we have one long-range force, Fg, that is pointing straight down. Okay, be careful, even if it's on an incline, gravity is still trying to pull the object downward. Okay, so straight down, towards the center of the Earth. Next is to decide what we do with the axes. Typically we use the x-axis to be horizontal and the y-axis to be vertical. If we do this in here, we'll have to decompose vector friction force and also the vector for the normal. So in cases where we're dealing with inclined planes, it's usually a good idea instead to take our x-axis along the direction of the incline, up or down, being positive, it doesn't matter, and then the y-axis perpendicular to that. So something like this. Then we can recopy our forces, and we have the normal that is now right on the y-axis, which is great, the friction force, which is right on the x-axis, and the only force that we have to decompose is the force due to gravity. To decompose the force due to gravity, I encourage you to draw a box around it. Remember, it should be a rectangular box, so something like this. Okay, and then on the 2 axes we have the value of the components. So this one in here would be Fgx, since it's on the x-axis, and this one in here will be FGY, since it's on the y-axis. And then the big question that always comes when we ask for an inclined plane is, where is the 37-degree angle? Is it in here or is it in here? Okay, so the next two slides I'll try to demystify this so that you don't make that mistake ever again. So we can use geometry to find the angle. Simple thing that you've seen in high school. So let me draw the FG vector. Once again, I'll make it super long and start it from the bottom of the object to make it a little bit more clear. So this basically in here gives you a triangle. And in this triangle, we know that this in here is a right angle, because that's an horizontal line and a vertical line. And therefore, this in here must be equal to 53 degrees. And we know this because the sum inside a triangle should be equal to 180. So 90 in here, plus 37, we're missing 53 degrees to get it there. Then you can add your axes. So we know that the x-axis will be matching the direction of the incline, so like this, and the y-axis will be perpendicular to that. So like this. Let me just move these a little bit so that they are all centered together. Okay. And then it should become obvious to you that the angle that is interesting, or the 37-degree angle I should say, is the angle that we have not with the x-axis, but with the y-axis pointing downward. So if we want to have, for instance, FGX, or in here actually we are looking for FGY. So if we want FGY, we have two options. FGY will be the part of the angle that is, let me add it in here. So if we do again the idea of the box, okay, the FGY is this side in here. That's my FGY. So I have two options. Either it's the side that is adjacent to the 37 degrees, which is the standard way to do it. So we can write it as FG cosine of 37 degrees. And you see we use the cosine even if it's on the y-axis, just because of where the angle is. Or we could also find it by using the 53 degrees if we wanted to. And then it would be FG, but the 53 degrees, you see the side that corresponds to FGY is opposite to the angle. Therefore, we need to use the sine. So we would use sine of 53 degrees this time. So both methods will work. It doesn't matter because cosine of 37 degrees is the same as sine of 53. If this is still confusing to you, you can take it to the extreme. We have a tendency to draw angle roughly at 45 degrees, but you can draw a super small or super large angle to help you out. So if we have the super small angle in here, then when you draw your y-axis will look something like this, right? Okay, let me just move it so that it matches FG. And you can see therefore that it's pretty obvious that when you do this, the angle that you're after, the angle that will be the same as the angle of the incline, will clearly be the one closest to the y-axis. Clearly the angle that we're looking for is this angle here. And the same trick can be used with the super large angle. So we can put our axis in here, and you can see that the angle that we're after this time will not be the small angle in here. The angle that will be the same as the angle here has to be this one. So we know it's always the angle of the incline is always the angle from the y-axis. Finally, the block that is pushed against the wall. So same trick as usual. We draw our circle around it. We have one contact with the wall, one contact with force F1. So from the wall, it's a contact force, so we're expecting definitely a normal force. But we're also expecting possibly to have friction. And in here, in order to keep the block at rest on the wall, we know that friction will have to point upward. A little bit like what we saw in the previous example with the inclined plane. And we have one long-range force, which is Fg. So when we recopy this on the free body diagram, we have Fg pointing straight down, and we know that the block is at rest, so right away we know that Fs has to have the same strength as Fg. We have one force on the positive x-axis, which is the force F1. And again, because we know the block is in equilibrium, this means that the force on the other side, which will be the normal force, will also be equal to F1. So we can find the answer right away from the diagram. But if we want to be a little bit more precise and clear, we can do the sum of force this time on the x-axis, even if we want the normal, because the normal is perpendicular to the wall, so horizontal. And on the x-axis, we see that we have F1 minus the normal is equal to 0, which means that the normal is equal to F1, or if you prefer, it is equal in here to 30 Newton. So that's a wrap for this clip. Make sure that you are aware that the normal is always perpendicular to the surface, and that to be able to find the normal, please get away from the idea that it's always equal to mg. What you really want to use are the sum of forces, and from the sum of forces, you'll be able to find the value. Alright, see you next time.